All right. I know the heckling will commence that I still haven't gotten your exam graded. I'm sorry, but now that I've got my graduation list submitted, I can sort of devote a lot of attention to grading. Everything else, though, is graded. I'll say that. My TA's been fantastic, so everything else is graded. So the only thing that's left is the exam, which come Monday, I'm really hoping to just knock that out over the weekend, and then we will be current. We will be up to date with grades in CE 312. The exam's the only thing we're missing. So again, my apologies for the delay in getting that back, but my goal is to get that done this weekend. How did homework 5.4 go? I'm just curious. That was the last shear enrollment diagram assignment. The Excel one, so. I'm hoping it should have been easier than what we did in class. That was the point. So, in terms of what we have left with shear enrollment diagrams, we have three sort of big topics. I have one that I sort of tacked on to the side near the end, but our three big topics are today's topic, which is the assessment of shear enrollment diagrams with concentrated moments. Okay, and how a concentrated moment affects the construction of a shear and moment diagram. The next one, which we'll do on Monday, is dealing with an internal hinge. Okay, because we haven't drawn a shear and moment diagram for beams with an internal hinge. With both of those topics, there's a very simple conclusion that you can make about what the shear and moment diagram should look like as a result. So topics 5 and 6 really do close the topic out conceptually. Lecture 7, I've got two things that I'm focusing on with Lecture 7. The first is shear and moment diagrams for frames, which is not difficult at all. It's just taking a shear and moment diagram that's this way and just turning it. That's really it. But I also want to talk about structural analysis aids or tools that you can use in the construction of shear and moment diagrams. Essentially what those are pre-derived formulas for basic loading scenarios. In this course, I'm trying to stretch your abilities and really get you comfortable with drawing shear and moment diagrams for fairly intricate and complex scenarios. But I mean, if I'm being honest, there's a lot of routine structural design that requires routine structural analysis. And so our last topic with shear and moment diagrams is going to be how do you handle those routine shear and moment diagrams, the ones that you draw over and over and over again. And you do that with some tools to make your life a little bit easier. Okay, everybody get the code? Does that poke on the shoulder? Does that poke on the shoulder? Okay. All right. Okay. Lecture 20. Believe that we've been in here. Oh, can you believe we've been here for 20 lectures already?
Yes. Yeah. How many left?
Well, there's, I think I have scheduled, there's 43. So, I think it's 43. But that also includes exams and things like that. Okay. Same relationship, the relationship between loads, shears, and moments. Same conclusion. So, I'm going through that part really quickly. The relationship between loads and shears, the relationship between shears and moments. It's all the same, okay? So what we're dealing with now is concentrated moments, okay? And the thing about concentrated moments is that they are really, really easy to deal with, okay? So the first thing I want to talk about is the relationship between loads and shears, okay? So how does a concentrated moment affect the construction of a shear diagram? The answer is it doesn't. Okay, and it doesn't because it's not a shear, it's a moment, okay? So when you're constructing the shear diagram and you see a concentrated moment, ignore it. Just ignore it, it's not there, okay? Now, what that's going to do is it's going to give you a little bit of a problem when you start looking at the integrals of your shear diagram. You're going to start computing the area under the curve for your shear diagram, but you're going to find it doesn't balance. It doesn't sum to 0 because the difference is the concentrated moment. So what that concentrated moment is going to be is a jump on your moment diagram, sort of like a point load, just a point moment. That's basically how it works. And the same idea works with cantilevered beams. So cantilevered beams are sort of on the extreme side of the shear areas not equaling 0, but the difference is the moment reaction. So just to assess this, we're going to, whoop, that would have been bad. About fell over. To assess this, we're going to do two problems, okay? But really what I should say is we're going to continue two problems because these are two problems for which we have already computed the support reactions. We did these problems earlier in the semester when we computed support reactions for concentrated moments. So the first problem is an overhanging beam. It has a concentrated moment on it, but it also has a distributed load. It also has a point load. So I really like this example to sort of make sure that we're holistically understanding everything associated with shear and moment diagrams because it includes it all, okay? So we have an overhanging beam that's a total of 45 foot long. It's 25 foot between support A and support B. We got the diving board effect all the way out here. We've got a distributed load, a point load, and a concentrated moment. Now we've got our reactions already solved for, AY and BY. We've got those here. I'll give you all a sec to draw this out, and we will get rocking and rolling. Okay, and again, we already computed these reactions. We already have them, so it's not like I'm throwing values at you that you've never seen before. Okay. Everybody with me so far? Okay. So we're going to start off with our shear diagram. Hold on. Oh, okay. I don't know what was happening there. My pen didn't seem to want to connect for some reason. Let's try it again. Okay, that works. Okay, so there's that. Okay, so we'll start off with our shear diagram. And again, shear diagram is going to be constructed the same way we've been doing it. So we're going to start at 0, and then the first thing we're going to do is we're going to jump up. To 15.2. Okay? Now, I've walked you through this up until now, so you tell me what to do from here. So if I'm at 0, I jump up 15.2. Tell me what happens. Let me throw some letters on here just to have something to reference. So we'll call this letter C, letter D, letter E. So tell me what happens on the shear diagram between A and C. I heard somebody use the word triangle. Okay, that's correct, but give me some more specifics. So what's going to happen between A and C? Goes down 30, right? So if I'm at 15.2, I go down 30, what's that put me at? Negative 14.8. So look something about like this. Maybe something about like that. Okay. All right, so what does the shear diagram look like between C and B? Just totally flat, totally horizontal, because there's no load. If there's no load, there's no change in shear. No change in shear means a horizontal line. Okay, so we're at negative 14.8. What happens from at B? So if I'm at negative 14.8, I jump up 24.8. That puts me at 10, right? So we'll go, I don't know, about like that. Trying to maintain the scale. Okay? All right. From B to D, what does it look like? Just flat, right? Okay, now we get to D, and we see something we haven't seen before yet on a shear diagram. We see the concentrated moment. How does that concentrated moment affect the shear diagram? It doesn't. So in the construction of the shear diagram, we ignore it, okay? So what does the shear diagram look like from B all the way to E? It's just flat. And then that 10 kip load brings us down. So if you want, we'll put a little point right here to say that's also 10. But again, how does the how does the concentrated moment affect the construction of the shear diagram? It doesn't, and that's it. Okay. There's your shear diagram. Pretty simple, right? Make sense? Okay. I am going to integrate. Now, I'll start from right to left, and I am actually going to split this up into two rectangles, left and right. So we'll integrate here and integrate here. So 10 times 10 is 100, 10 times 10 is 100. So we'll put plus 100 here and plus 100 here. And my main reason for splitting it up is it didn't affect the construction of the shear diagram, but these areas are used for the moment diagram, and it's a moment. So I'll have a value here and I'll have a value here. All right. What's 14.8 times 15? Or negative 14.8 times 15. What's the area of this rectangle right here going to be? Negative what? Negative 222. Okay. All right. Sound good? So how do I get, how do I do this and this? We've had these problems before, so how do I do that? Well, let's ask it this way. What's the slope of this line? The negative 3, because that's the magnitude of the distributed load. So what I need to do is I need to figure out this distance right here, and I need to figure out this distance right here. So we'll call it x2 and x1. Okay? So how do I determine x1? How do I do that?
Divide 15.2 by -3.
There you go, 15.2 over 3. And the negatives don't really matter, but you're 100% right. You're going to take the jump in y divided by the slope. So this is 15.2 over 3, which, I mean, is what, like 5.07, something about like that. And this one's going to be 14.8 over 3, which is something like 4.93. Does that make sense? So if that's the case, somebody tell me what the area of this upper triangle is and the area of this lower triangle. And we'll just say like 1 decimal place. I think that's good enough. Like, what's the area of this?
38.45.
So we'll say positive 38.5. And we'll call this one what?
Negative 36.5.
5 seconds. Negative 36.5. Okay. Okay. All right. Now, before we start going into the moment diagram, I do want to make a point. Okay. So what happens when we sum up our areas? Like, let's sum up these areas. So we're going to have this, and this. Okay, so we have 38.5 minus 36.5 minus 222 plus 100 plus 100. So what is that sum? Negative 20. Have a second?
Yeah.
So what has it been for every problem we've been doing up until now? It's been 0. In this case, it's not 0. It's negative 20. So, why? Do we see the value 20 magically showing up on this problem? Why, by golly gosh, do we do? That's the 20-foot kip moment, right? I use very technical terms. You place concrete in my by golly gosh gee courses. I love my job. Okay. So this is negative 20, but it needs to be 0. Okay? What that means is that this 20-foot kip moment is going to be a jump upwards, right? Because if we were to construct the shear diagram and ignore that, we would not end at 0, we would end at negative 20, right? So this moment needs to bring us up, right? So when we get to this moment, it's just going to be a sudden jump upwards. Let's see how that works, okay? So let's construct our moment diagram. Okay. All right, so what does the moment diagram look like from here to here? Between these points right there, what does the moment diagram look like? What's the shape? It's a parabola that sort of does that thing, right? So it's going to go up and crest and then come back down. The magnitude's going to be right there. So we're going to go up 38.5, down 36.5. So like over here we're going to be at like 2, right? So it's going to sort of do this thing. It's going to like something like that. Does everybody see how I did that? It's like we'll go a lot to a little right there, little to a lot, come down to 2. And this is all one parabola. I'm just indicating where the maximum is right here. Sound good?
What exact number did she get to get the 36.5?
What's that?
The 36.5, like what two numbers did she multiply?
Okay, this area is negative 36.5. Okay, so how do we get that? We do 1/2 of the base times the height.
Okay.
And then same thing over here, 1/2 of the base times the height. So 1/2 of this times that is 38.5. 1/2 of this times that is 36.5. So we start at 0, go up 38.5, then down 36.5, so 0 that to 2. That's a good question. Everybody okay with that? All right. Now, if I'm at 2 and I drop 222, what am I going to be at right here? Negative 220. And what does that path look like from here to here? It's linear, right? So this is like, I mean, if we're drawing this to scale, this is a drop. I mean, it's really going to go like all the way like down here, like really far down. I mean, I know that seems kind of silly, but that's what it looks like. Okay? Make sense? And then I'll go ahead and just indicate what is the slope of this line? Negative 14.8. So we'll say this is quadratic. And that's linear. So now what does the moment diagram look from here to here? Is it just a straight line? Well, it's linear, but it's going to be discontinuous, because if we go up 200, we're going to be at -20. What's happening is we're going to go this, then a jump up, then that. Does that make sense? That's what's going to happen. So we'll do that. And that. So we'll go from 220 or -220 up 100 to -120, get the jump to 100 or -100, back up to 0. And that's what our moment diagram is going to look like. Why do we have this jump? Because right there is where the moment is. Okay. All right, does that make sense? Yes.
So if the moment is like a jump up or jump down, is that based on the direction of the moment?
Yes, it is. So that's a good question, and the answer to that is yes. Okay. A lot of times when we're first learning about shear and moment diagrams and concentrated moments, I find it easier to figure it out this way. But we'll be able to answer that in a little bit more specificity when we talk about deflections. Okay. But here's what I will say, and because it's an overhanging beam, it's sometimes a little difficult to see. But I'm saying that because of the loads that are already on this beam, what this moment will do is increase the positive bending in that location. It sort of causes the beam to want to smile more there. We're not in deflection land yet, so we're not really talking about beams deforming. But when you start looking at it from that perspective, you'll see either smiley face bending or frowny face bending. And so we'll be talking about that here in the next couple weeks. So for now, the easiest way to figure it out is to just look at it like this way. I'll also say that the next example we're about to do, we're going to start to lean into that deflection land just a little bit, and so you'll see a little bit more there. That's a good question, though, and it's a question I can give you a half answer on today. A full answer on here in the next couple weeks. So, sound good? Okay. So, this lecture regarding the construction of shear and moment diagrams for concentrated moments would be incomplete if we did not look at a cantilever beam. A cantilever beam, like I say this, I think cantilevered beams are among the easiest structural analysis problems that we deal with just because of the nature of the problem. They also are the most extreme in terms of like shears not balancing to 0 and whatnot, because they certainly won't on problems like this. So, again, we've already done the reactions for this problem, and as we mentioned before, reactions for concentrated beams are also fairly easy to compute, because you don't really have to be strategic. You don't have to go, well, we need to sum moments first so we can isolate this reaction, then sum verticals to get the other one. You don't really have to worry about that with a cantilever beam, because you can just solve for all the reactions all at once, which we've already done. One thing I will remind everybody, we do have an inclined load. We have, and I did sort of sneak that one on here a little bit, this inclined load. Let's talk about that. Let's really talk about that. Okay, this inclined load, okay, let's split this up into X and Y components. So if I split this up, what's the Y component? And what's the X component? What's the Y component? This is a 10 kip at a 3 to 4 slope ratio, 3, 4, 5.
8 kips.
8 kips is the vertical, and the horizontal is 6. Okay. So the first point I want to make regarding the construction of the shear and moment diagrams is that a shear diagram is just that. It's shear. It's transverse loads. When I say transverse loads, I mean perpendicular to the axis of the member. Okay? So this 6 kips is parallel to the axis of the member. That's why we call it an axial load. Okay? Remember, truss members only carry axial loads. They only carry either tension or compression. So this 6 kips, what is it doing to the beam? It's compressing the beam right here, okay? So, for example, if we wanted to do this, and I'm not making you do this, but if you notice, do you notice how on the homework assignments I've been saying don't draw the axial force diagram, just draw the shear diagram and the moment diagram? You know I've been saying that? Let's talk about what the axial force diagram would look like for this beam. And I'm actually going to draw it. So if I wanted to draw an axial force diagram, so this would be the forces along the axis. I propose that from here to here, is the member experiencing compression? And it's experiencing what? 6 kips in compression? So what I would say is that the axial force diagram would look like this. But that's what the axial force diagram would look like, that we're experiencing a compressive force in part of the beam, but out here, there's nothing on the beam that's squishing it. Okay? That's an axial force diagram. Okay? We've actually sort of been drawing axial force diagrams this whole time because the truss solutions, those are axial forces. But really all it is it's just a constant axial force along the entire member. So for example, if you have a truss element and that truss element is experiencing 20 kips in tension, it's just a positive 20 across the whole member. That's it. Okay? That's an axial force diagram. So in case you were wondering, that's it. There's really not a lot to say. Okay? But we're interested in a shear and moment diagram. Shear diagrams are transverse perpendicular to the axis. So let's draw the shear force diagram right now. Okay? So, tell me what to do. I start at 0, what do I do? For shears. Go up 28. What's it going to be like from A to the middle? Flat. And then I get here, I'm at 28. How far do I go down? If I'm at 28, how far do I go down? 8. And that'll put me at 20, flat. The 20 brings me back down. That's it. Okay? So that's our shear diagram in a nutshell. Okay? Now if we integrate this, the integrals are pretty easy because on the left we have 28 times 10. This is going to be 280. This is going to be 200. Okay? Now, this is sort of what I meant though when I said the polar extremes. Do the sum of those areas add up to 0? Not even close, right? Like the sum of those areas are positive, right? They are positive, and the sum of the areas is what, 480? Okay? Where am I going to get that balance? I'm going to get it from the reaction. So what's going to happen is this reaction is going to be a sudden jump downward, and then we're going to bring it back up. Does that make sense? And then I kind of want to go back to your question after we draw this. Okay? So when we construct our moment diagram, first off, are there any parabolas on this moment diagram? It's all straight line segments, right? Because we have constant shear, so we have linear moments. But what is different is that we're going to start at 0, and what are we going to do right here? Like, what's the first thing that we do before we start drawing out?
You go up before it.
Well, let's talk about that. Do we go up or do we go down? Think about it. So let's ignore the moment. Let's just ignore it. Let's say it's not there. If this moment didn't exist, what would you do? You would go from 0 to 280, from this to 480. But there's nothing here to bring you down. I'm saying you need to start negative, then go back up. Does that make sense? Okay, and then I want to get to Mr. Fry's question here in a bit. So we're going to start at negative 480, then come up to negative 200, then go to 0. Okay. Does that make sense? Tell me if it doesn't. Everybody okay with this? Okay. Now, let me just sort of go a little bit into the question that Mr. Fry brought up earlier about the directions. Okay. And I want to talk a little bit about bending and deformations. We're not in deformations yet, but this is a natural place to at least start talking about it. Okay. The loads that are applied to the beam, like, ignore the reactions. Let's just talk about the loads that are applied to the beam. Ignore the shear diagram, the moment diagram, all this. Just look at the beam, look at the loads. Is the beam going to deflect upwards, or is it going to deflect downwards? It's going to go down. We all agree with that, right? Okay. Now, this is a beam, so it is going to flex in a curvature like bending. I mean, like there's no real magic behind that. Go grab a ruler out of your backpack, hold it with one end, and force it. The thing sort of curves down like that, right? Okay? So if you were to apply a smiley face versus frowny face image in your head, do you think that the beam is going to be smiling at you, or do you think the beam is going to be frowning at you? It's going to frown at you, okay? We have so smiley face, frowny face is the simple way of describing a more technical version of the term, and the technical version of the term is positive bending versus negative bending, okay? Whenever your moment diagram is negative, like it is right here, we have a completely negative moment diagram, okay? The beam is frowning when it deflects. It is experiencing a negative curvature, okay? It's frowning at us. Okay. Now your question was sort of like, can you just look at the moments and decide whether or not the moments are going to be positive jumps or not? Yes, if you can relate that to the deflected shape. Okay. What I'm saying is that for this cantilevered beam, because I know the beam is going to totally deflect, you know, in that fashion, that's what that means, that it's going to be a negative jump. Okay. For the last problem that we just did, it's a little trickier, okay? And the reason it is tricky to do that for the last problem, like let's take a look at that problem we just did, okay? I think it's a little bit trickier to just sort of perceive that that's a positive jump versus a negative jump, because look at the shear diagram and look at the moment diagram. It's honestly kind of complicated. And what I'm saying is that the deflected shape of the beam is also kind of complicated. It's not just a simple smile or a simple upward shape or whatnot. In fact, the deflected shape of the beam, like if I were to try and sketch it out, probably looks something kind of like this. It's probably going down, probably doing this, and maybe something like that. You know, that's kind of what it looks like. What I'm actually doing right here is I'm doing what's called drawing the elastic curve, okay? It's sometimes called drawing the deflected shape. That's another thing I've been putting on the homework assignments where I say don't worry about drawing the deflected shape. We're going to talk about that later, okay? But what I'm getting at is when you combine that with the deflected shape, which we'll talk about later, it's a little bit easier to ascertain whether or not this is jumping up or this is jumping down. For the purposes of just learning how to deal with them right now, I think the much easier way to figure out which way it's going to jump is to just look at your areas. This is a sum. The sum of these areas are negative, which means the jump's got to be positive to bring it back up into equilibrium. Okay? Does that make sense? So we'll get to the deflected shape, the elastic curve, and beam deflections. We will get to it. We'll do it later. So there are rules for constructing the elastic curve. We're going to discuss those rules a little bit later. But for right now, I like sort of doing it one step at a time. Like one thing I didn't really, like if I was writing a structural analysis textbook, I wouldn't not talk about elastic curves, but it seemed a little strange, like if you read the book, so chapter 5 is on shear and moment diagrams, chapters 6, 7, and 8 are on deflections, but you're talking about deflected shapes in chapter 5. It's like you're talking about deflected shapes before you talk about computing deflections. It seems a little backwards. I feel like you should take it one step at a time. That's just me, so. Yes?
When we're doing these shear and moment diagrams, does the direction of the moment not matter?
No. Yes, it does. Yes, it does.
Okay.
Let's talk about that. That's a really good question, okay? So your question is, does the direction of the moment not matter? Of course it matters, okay? But here's the thing to keep in mind, okay? So let's assume that this moment was going the other way, okay? I propose to you it would not be a jump up. It would be a jump down. But that's myopic just thinking about that, because you're right, it would be jumping in the other direction. But these reactions would also be different. You would have a different shear diagram, you would have a different moment diagram. I promise you that for this beam, if all we did was look at this beam in a vacuum and switch the direction of that moment, we would jump in a different direction. But if all we did is jump in a different direction and didn't change any of the other values, then it wouldn't sum to zero. I'm saying that the reactions would have to change in accordance with that to balance everything out. Does that make sense?
Kind of.
So, like, here would be my suggestion, okay? Take this problem and do it again, switching the moment. But delete these and recompute them. You will get a different value, okay? Like, let me show you something. Let's answer it this way. Here's the problem. This is when we did this problem. We did this problem, okay? These are the reaction computations for this beam, okay? See how we got 24.8, 54.15.2? Here's what I'm saying. This 20-foot kip moment was over here. What if it was over here? You would get a different answer. You would get a different answer here, and because you got a different answer here, you would get a different answer here. The reactions would be different. That affects the shear diagram and the moment diagram.
Okay.
The jump would go in a different direction, but everything else would change too.
So when we're computing the reactions, like say, counterclockwise is positive,
Yeah.
but when we're doing the diagrams, it's reverse, basically.
What? It's not that simple. That's why I'm suggesting look at the areas. That's why I'm suggesting calculate the areas, and whichever, that's why we did this, okay? So when we go back to this problem, I'm saying for a beam like this, because you've got overhanging, because you've got loads in different directions, figuring out which direction is actually a little tricky. The easiest way is to say the sum of the areas are negative, so the jump has to go up, okay? I'm saying that you're asking, well, what if you just flipped it? I propose the sum of these would be positive, and the jump would go down. But I'm also suggesting the reactions would be different too, okay? And the other thing I'm suggesting is that just eyeballing those would be different if the moment was over here, or if the support was over here. It makes the problem totally different. That's what I'm suggesting, so.
Okay.
That's a really good question, though, so. Any other questions? This is good stuff. I really like this. Y'all do this more often. I like this. Make me earn my paycheck. I love this stuff. See, here's the thing. He asked that question. I guarantee, as soon as he asked it, there was like 10 people who were like, yeah, I wanted to know that too. So don't be shy. Ask. Any other questions? I've got 2 practice problems for you. Due Monday. I'll say one thing about one of the problems, okay? I'll go ahead and preface you with this. So one of the problems has a point load and a moment in the same spot, but that shouldn't matter. Because again, when you're drawing the shear diagram, you just don't look at the moment, all right? So I did that on purpose. I wanted to see what you came up with. I do think, though, these are odd-numbered problems. I know somebody asked that. Was it you that asked that about the? I think they're odd number. I think they both are. I don't think that's the case on the next homework assignment. I know. I'm sorry. That's all I got, everybody. You're getting 9 minutes of your life back.